So I welcome you students for our discussion on resonance. Before you do that, check out this animal. This is called a unicorn, an imaginary animal which has mystical powers, the healing properties. It can take you to deep skies. It is very familiar in Indian literature. Unicorn. Try to browse in the internet. So many people are familiar with its picture. This is another imaginary animal, dinosaur, and it is said these are not existing now. This dinosaur and unicorn, if they genetically combine, people say you get this rhinoceros. Suppose you have never seen rhinoceros, but you know the picture of this, you know the picture of this, you are asked to construct the picture of rhinoceros. Can you do that? Such an attempt is made when we are discussing resonance. In resonance, we are trying to construct the real structure of a molecule from some imaginary structures. Now, let us exactly examine what is resonance. Resonance implies flow of electrons from one location in a molecule to the other. This flow is called a delocalization. And mind you that this flow of electrons happens in the ground state itself, involving complete shift of electrons. And notice that you can write several possible structures using this, but which electrons are involved means orbital electrons, which are in the form of lone pairs, or pi electrons, and the electrons can go from one pi bond to generate a new pi bond, or lone pair can be converted to pi bond, so on. And what are the conditions for this to happen means, if the molecule is involving second period elements like boron, carbon, nitrogen, oxygen, all they must undergo sp or sp2 hybridization, and the molecule must be flat with alternate double bonds or with conjugation. What do you mean by conjugation? By conjugation we mean, in this molecule like 1,3-butadiene, you have a double bond, single bond, double bond. Can you see? In benzene, double bond, single bond, double bond, single bond, double bond. Alternate positions. You can have here lone pair, single bond, double bond, single bond, double bond, single bond, double bond, single bond. You have here, this is negative charge, single bond, double bond. Here in aniline you have lone pair, single bond, double bond, single bond, double bond, single bond, double bond. Even in this allyl carbocation you have double bond, single bond, positive charge. Allyl carbanion has double bond, single bond, negative charge. Allyl carbocation, positive charge. Allyl carbanion, negative charge is in alternate positions. Allyl free radical, double bond, single bond, unpaired electron on carbon. Vinyl chloride, double bond, single bond, empty d orbitals of chlorine. All these systems are said to be in conjugation. In conjugated systems, electrons can flow. The flow of electrons can be represented using a curved arrow method of Robinson. If you put the pi electrons like this, they will become lone pair. These two changes are represented by two canonical forms. This move is called a legal move. You can make only some legal moves to show the movement of electrons. The pi electrons can go over here to make a double bond here. Due to this new addition, it got minus charge, it got plus charge. Okay. Notice that you can also show this can come down here, and you can write another canonical form like, right, it got minus charge, it got plus charge. All these are legal moves. Okay. Now the question is, to which extent this resonance can happen? In a molecule, this resonance can happen to across millions of carbon atoms, but if there is conjugation like double bond, single bond, double bond, single bond, double bond, single bond. If conjugation is there, this can extend over millions of atoms. You please notice that the hybridization of second period elements involved must be either sp or sp2 for resonance to happen. If it is a third period element like phosphorus sulfur, sp3 hybridization is okay. You can see the resonance in phosphate and sulfate ions. Sir, what happens if there is resonance? I would say that due to resonance, carbonate ion can have resonance. You can write three possible structures for carbonate ion. These are all called canonical forms. Notice that they are indicated by a double-headed arrow, but neither of these forms have real existence. Real carbonate ion is a hybrid of all these three. So also for ozone I can write two canonical forms. And you can think of, for phenoxide ion, we can write as many as 5 canonical forms. And as many canonical forms you are writing, molecule is getting greater stability. The stability is reflected in lower heat of hydrogenation and lower heat of combustion. And also it can bring about a variation in bond lengths. Further details of resonance, how it can bring about all these things, we see in our next video. But mind you that always resonance demands a presence of the system in conjugation, alternate double bonds. Okay, with that note we conclude. Thank you very much.